Yes, yes.
Yes, fine. Good evening. Let me start with a brief introduction of why wind tunnels. Okay. Before moving into the session, I have a humble request to you people. Please mute your microphones and just press this screen tab wherein you will find this pin button, pin your screen such that if someone is disturbing in between, you will not be distracted by someone's presentation. So please pin the screen. If you have any questions, please go ahead and comment in chat. My student and friend Mr. Murukesh is available online, and he has done some work on wind tunnel, so I will be presenting his results too. So he might be helping in discussing about the answers for your questions and doubts. So before moving into the section, I have a brief note about the webinar. So there will be no background, there will be no transition in slides. Rather, I will be only focusing on contents since it's a webinar. So please take this into account and pay attention to the content. Okay. Before starting our core topic, I have to thank my professors who taught experimental aero and gas dynamics and who allowed me to work on various setups to build different tunnels for different types of turbulence measurements or flow measurements. And I had a good opportunity to work with NIL scientists and DRDO scientists in IIT Madras. And thanks to my students who built a couple of tunnels in SRM, and I will be presenting those results in the coming slides. So what are the takeaway things from this webinar? So basically, if we want to know about a wind tunnel, we have to understand what a wind tunnel is, and then what are the parts, what are the types, and then how does it work. And if we want to build one, we should understand exactly each and every part, how it works, what is the physics behind it. So in this webinar, I will be concentrating more on the physics of flow, how to generate it, what it does to the flow. So each and every part we will discuss in detail about the physics. So mathematics or formulas I will not discuss, but I will tell you where you can find it and how you can get those calculations done easily, because those are straightforward. Rather, we have to give more importance to the physical aspects. So I will be discussing about tabletop wind tunnel and an atmospheric boundary layer tunnel. So I will be giving you an example of how a wind tunnel was built in our laboratory. So coming to the first point, the definition of wind tunnel. I hope most of you might have used wind tunnel in your aerodynamics laboratory or advanced fluid dynamics laboratory. Typically we do some experiments there, and wind tunnel is defined as a device, especially a test rig if you are continuously doing some test in the wind tunnel, or we can call it as a device on an experimental setup, wherein a person can produce a controlled or conditioned flow. The flow can be of any fluid, it can be water or it can be air, based on what kind of study we are going to do in that particular device. If we are using air, it will be about aerodynamics. So wind tunnel is a device that produces some conditioned flow or controlled flow of air to study about aerodynamics. So hope most of you know about aerodynamics. If you do not know what is aerodynamics, aerodynamics is a study of flow over bodies or bodies moving inside a fluid, and how interactions happen, what are the forces and moments generated. So we will be dealing with these in aerodynamics. So mostly wind tunnel is a device dedicated for aerodynamic study. So where we use wind tunnel, why we use wind tunnel, and what are the things we can get out of a wind tunnel. So wind tunnel most probably we see in aerodynamics laboratories, aviation people use, and some atmospheric people use, and you might see usage in automotive aerodynamics, where people study about flow over cars and so on. And typical usage of wind tunnel is to find pressure values from the objects which we keep inside the wind tunnel to test it, such that we will find pressure distribution over the particular body, and we want to know about forces and moments generated on the body That's where this becomes one particular aspect. And one more aspect, if you want to know what is the kind of flow field that is happening over that particular body inside that wind tunnel, we can go for visualization techniques. There are n number of visualization techniques that are available to see how the flow field is. So these are the typical requirements which we have and for which the wind tunnel caters. So if you know what is a wind tunnel and why we are using it, then you might ask what are the types of wind tunnel available here and how we can classify it. So if you see the classification of wind tunnel, it can be done based on the flow speed. This is the first part which I have mentioned. Based on flow speed means usually we classify flow speed regimes into subsonic flow, transonic flow, supersonic flow and hypersonic flow with comparison to the speed of sound. So when the flow is comparable to the speed of sound, it is sonic flow, and above it it's supersonic flow. This is typically expressed by a non-dimensional number called Mach number. So if Mach number is 1, it's called sonic. Mach number is greater than 1, supersonic. Mach number greater than 4 or 5, it's called a hypersonic flow. If it is typically less than 1, we call it a subsonic flow. And if it is typically less than 0.3, we will say that the flow is completely incompressible. So based on flow speed, I think we can classify wind tunnels into various types. And based on flow direction, we can say that whether it is blow down type or whether it is suction type, like whether we are taking in air from the atmosphere and conditioning it and allowing it to the wind tunnel and then discarding it to the atmosphere, or the other way wherein we take air, we push it and test it and then discard it. So two types of flow direction based classification is also available. Then based on looping, if we have say the wind tunnel which is open type, that is it's like a duct wherein two ends are open, you can take air from atmosphere and you can discard in atmosphere again, it is called open loop wind tunnel. And if this duct is completely closed like a circuit, and it is called closed circuit wind tunnel. So these are the two types. If you ask me what is the difference between these two, if you want to have a general wind tunnel wherein you can take atmospheric flow, it is open circuit type. And if you want to say avoid disturbances from the ambience and you want to have a particular type of fluid inside the tunnel wherein that flow is keep on circulating inside the tunnel itself, it is closed loop tunnel. Suppose if you inject some tracer particles and you don't want the tracer particles to be discarded to the atmosphere, that time you can go for closed loop wind tunnels. And there are a few wind tunnels based on applications or design aspects. That's where I mentioned a tabletop tunnel and atmospheric boundary layer tunnel. Hope I have given you a brief idea of what is the classification of wind tunnels. Moving ahead, so this particular webinar, I am going to concentrate only on one particular wind tunnel. This is a subsonic wind tunnel, which we have seen in our labs, but we might not have seen this in a perspective where I see things differently from how other people see. So I will be discussing about those aspects mostly in terms of physics. So if you understand this aspect, I think this is going to help you to think in your own way how I can come up with a wind tunnel by my own from the particles available around us. That's how the topic is. So this is a typical subsonic wind tunnel which you have seen in your laboratory, or if you Google you can easily find it. Thanks to Mr. Gaushik who designed this in a very short time for the webinar. And if you see this picture on the extreme right side, I have mentioned the blue arrows, and these blue arrows is the flow which we are taking from the ambient conditions, that is from the surroundings. Then you have a constant area section. This is the flow conditioning unit, and then moving forward we have a test section, and then we have a diffuser, and then we have a motor. Inside this diffuser we have a housing within which a fan is placed, and this is a typical subsonic wind tunnel. With this we have associated equipments like pressure manometers or digital manometers or load balancers. So we have a number of associated equipments, like also we can have visualization based equipments. So wind tunnel along with its associated equipments are called accessories we can use to study aerodynamics. So I hope this picture gives you an overall idea for everyone how a wind tunnel will look like. So paths of a typical wind tunnel. So I have shown you the paths in the schematic. So I can explain one by one. There is an intake that is on the extreme right side where I showed the arrow. Just next to it on the wind tunnel, first part is the intake, and then we have a flow conditioning unit. That's the constant area tube, and then followed by a contraction section, which is also included in the flow conditioning unit. And then we have a constant tube again, which is the test section where the models are housed. Then we have a diffuser, and then finally a fan, which is for the source of the flow. So what does the flow conditioning unit consist of? So if you consider a wind tunnel, the definition itself, I expressed a particular phrase wherein we are going to use a conditioned flow or controlled flow. So how to condition the flow or how to control the flow is basically based on how you tweak the fluid flow. So control is about speed. So if you have a motor connected to fan, and if you have an RPM controller, you can control the speed wherein the velocity of the flow can be controlled. That is a controlling aspect. The other aspect is about the conditioned flow. The conditioning aspect is what I am going to discuss here in this flow conditioning unit. So the flow conditioning unit typically it has the intake on one end and test section on another end. So in between you have a constant duct within which you find honeycombs, grids, and the end of this constant area duct you have a contraction section. So this is going to condition the flow. So why we have to condition the flow? That's the first question arises when we discuss about flow conditioning unit. So if you see typically in a room or a hall, you might find people moving around or fans switched on, and there are say differences in temperatures if you operate an air conditioning unit, or there might be gradients of thermal aspects. So you might be finding some flow that is happening inside that particular environment. The flow can be turbulent, laminar, flow can be swirling, flow can be fluctuating, whatever random characteristics you want to see, all characteristics might be present in the ambience. So taking this into account, we don't want to take all the disturbances into the wind tunnel, so we want to avoid all the disturbances. That's where we are going for conditioning the flow. So the conditioning the flow is done by these three parts in the flow conditioning unit. So if you essentially design this particular flow conditioning unit in a perfect way, you will be having a perfect flow in your test section. So that's where I am going to emphasize more on flow conditioning unit. We will see part by part. The first part, a honeycomb structure. You might know what is a honeycomb structure. Usually this honeybees, they have wax collected from flowers, and they come up with a structure which is almost a hexagonal in shape, and you have multiple hexagons added together, and this is found in trees at taller locations, and you might see that it's a tubular section inside a particular hexagonal cell, and this honeybees store honey inside that. So that's where the honeycomb name came from. So if you take a typical honeycomb, it can be of any cross-sectional shape. It can be a square, it can be a hexagon, it can be a triangular, it can be circular, and so on. So if you take a particular cross-section, if you allow a disturbed flow, here in this particular slide, I have shown on the left-hand side that is there is a swill flow which is shown by a rotating symbol. This rotating mass of fluid, if it passes through the honeycomb, it is conditioned and it is made say uniform into unidirectional flow. So that's where on the right side you see a parallel level of flows happening from each and individual cell. On the bottom side I have given, if we have a tubular structure at each and every location, how this rotating mass of flow is getting reduced, and then finally how it comes as a unidirectional flow. To know about how this swirling mass of flow is happening is, suppose if you take a table fan and if you allow that flow to happen, and if you see how the flow structures are, that is, if you make visualizations, you might find helical coils of vortices that is moving from the fan, and this might creep into the wind tunnel. So you really don't want swirling type of flows. That's where if you have a tubular structure, if you allow the swelling flow, the faces of the structure or the wall of the structure will try to reduce this radial flow type and convert that into axial flow type. So that's where on the bottom side I am showing this here. That is, there is a rotating mass of fluid which is moving into the tubular structure. That is the honeycomb's individual cell. At each and individual levels or each and individual cross section, you might find this rotating business is getting reduced, and then finally you have an output that is completely unidirectional. So to say simply, what honeycomb does to a flow is it converts the swell flow into unidirectional flow or an axial flow. That's it. So if you have this concept registered in your mind, I think you will know how to use this honeycomb in an appropriate place. So the other question will come to our mind is like, can I have this length of tube? How can I decide? Can I take a long tube or can I take a short tube? Something like that. You might have questions. So typically, how we will discuss about this length is we do not say directly in dimensional quantities. Rather, we will be indirectly dealing it with non-dimensional numbers. That's where we discuss about aspect ratio. The aspect ratio is about this cross-sectional parameter to the length of that particular tube. So if the length of the tube is longer, aspect ratio is higher. That's where if you have a aspect ratio of this honeycomb, typically from 5 to 12 or something like that, then your filtering of this swell and converting that into axial flow will be most appropriate or most optimum. So if you have a shorter length, what happens is, if you see this bottom picture, you might know as it enters, only partial swill might be reduced and you might get remaining swill as such as an output. So if you have a lengthy one, this tubular structure, you might be creating shear inside this particular tubular structure based on the wall, and also there might be a pressure loss. So lengthier the tube, more the pressure loss will be. So you should not go for too much length. That's where you have this thumb rule, which you can get it from books or wind tunnel sites, and you can go for those aspect ratios for your wind tunnel which you design. So hope people might have got about what is a honeycomb structure and how it is useful. So the next part is the grid. So grid is typically a mesh-like structure which you are seeing here on this left side. So the individual square elements within which the flow is possible, and in between two square elements, that is the metallic structure, wherein you can see this as multiple thin cylinders weaved together and with some specific gap between those thin wires, and these wires behave like a mesh, and this gap between those two wires, you can find it as a square passage, and within which or through which the flow can happen. On the right side, I have shown typically a zoomed structure of this particular part here, and a particular cell. If you see this within this particular cell, I have kept a smiley within which the flow can move through happily. So what about this particular zone then? This particular zone is the metallic zone where these wires are there, and this might be blocking the flow. So essentially, if you have a grid, you have to decide about what should be the passage between the wires, what should be the wire thickness, what is the separation, and what is the porosity. So you have to see what kind of friction it can create or what kind of pressure losses it can create. So you can decide about the porosity, and you can decide about the vertical structures which can pass through this particular grid or mesh. So knowing about different flow types, especially the random fluctuating flows which has the swirl or vortex or eddy, I will tell you exactly what those are. And if these are passing through this grid, it might be broken down into smaller pieces. For example, I will give you a typical example from a household. When we are making a roti, what we will do is we will take flour and we will have a sieve
that is a typical mesh structure. We pour this floor over that sieve, and then we shake it to get fine particles on the bottom side, and there will be big blobs which are filtered by the sieve. So typically, if you see the finer particles are passing through this particular sieve, like how the smileys are placed here in the slide, so which will be happily moving through. The blobs which are bigger than this passage will be blocked and it will be held up. So if you see a typical flow which has all the disturbances, which means a vortex or a eddy structure, it will be completely three-dimensional, and it might be a rotating mass of fluid. You can treat it like a blob. If a blob is bigger than this particular passage, this blob will not be able to pass through that particular passage. So if there is an incoming flow with the blob, and the molecules behind the blob will be pushing through this particular passage, such that you think the same sieve with the bigger blobs of wheat flour, and if you press it from the top, again this big blobs will be broken down into smaller pieces. That is, the powders will be passing through the sieve. That's where the pressure gradient or the flow which is driven from the rear side or pushed from the rear side, these big blobs of rotating fluids which will be pushed through this particular mesh will be broken down into smaller and smaller blobs. So this is one particular aspect. Why we want to break down this bigger blobs of rotating flow into smaller blobs is, like this bigger blobs of fluid which is rotating, it has some energy. It will be keep on rotating till it sheds its energy. Like if you have a typical sphere, it has a surface points. So by rotating for one rotation, it might shed out these particles by sharing energy to the surrounding say particles which are stagnant. And typically it takes multiple rotations or revolutions to shed almost its energy so it might take a longer time for this disturbance to get reduced. So if you want a faster reduction in disturbances, you can use a grid, breakdown into smaller blobs. The smaller blobs by fewer rotations, it might shed its energy, and it might lose its energy content, and finally it will become a smooth flow. That's where this grid is useful. So going into a typical explanation for this grid structure, I think I have given an analogy and I have given a basic explanation. So what is the physical background of this? If we want to see in terms of fluid flow physics, I have to go to next slide to explain about flow over a cylinder and flow through a gap, or flow through a nozzle or an orifice. So the left picture shows flow over a particular cylinder. A circular cylinder I have chosen, and this circular cylinder, why I have chosen is, typically if you see a mesh or a grid from a market, if you purchase it, you might see this individual mesh structure, or this grid structure having this thin wires. If you see the thin wires cross section, it will be like a circular cylinder. So if you allow flow over the circular cylinder from your fluid mechanics perspective, you can easily find that at typical lower Reynolds numbers, you might find vortex shedding pattern happening behind the circular cylinder. So the typical flow is like, it starts from the initial point on the surface of that circular cylinder, that is from the stagnation point. As it moves towards the aft side, the pressure gradient causes the separation of the flow, and thereby it starts producing vortices of this nature. So you might find alternative vortices shedding like this on the bottom side, and from top side it might be shedding on this particular aspect. So typically one vortex sheds from this cylinder, and then after this vortex moves out, and then another vortex sheds. So this is only about a separated or isolated cylinder. So this is one aspect to see. Suppose if you have a grid or mesh, you might find multiple this type of cylinders in three dimensions weaved in, and you are seeing gaps, and then you are seeing this blockages by this metallic cylinders. And typically if you consider a gap between two cylinders, you might find it as a passage or orifice, or in other terms you can see it as a nozzle. That's where I have this particular place on the right side between two slides. If you allow flow to pass through, it will be like a flow through an orifice. It will be like a typical jet flow. So the jet flow is a simple flow type wherein if you give more energy to the flow, or if you pump in energy, or if you accelerate the flow by restricting area, that's where the nozzle part comes in. So you might see on this aspect, the area might be restricting, and exactly at this midpoint, you might find the minimal area. So you might treat it like a contraction, and this is going to accelerate the flow. If you accelerate the flow through this passage, the flow which is coming out of this part, it might be spreading laterally like this outside the cylinders. So this is called jet flow. You might find what is happening in jet flow also, because this place you find maximum velocity, and this place you might find the minimal velocity. That is, the stagnant fluid will have zero velocity. So there is a velocity gradient between the center passage and this particular place. That's where you have this vortex happening, which is curling like this, and because of the convection moving towards the right direction, and this vortices shed, and then it moves like this. So now you have multiple such cylinders which forms the grid. If you see in the cross section, so there might be one grid here, this cylinder will be here, and another cylinder will be here. So you might find multiple flows happening from different passages. So these flows interact in the downstream region. So if there is another flow, this flow is going to interact, which means there might be another flow which is happening from this way. So this vortex and that vortex, it's going to interact. So when these vortices interact, what will happen? I will give an analogy here, then you will understand. If you take two laddus in two hands, and if you hit these two laddus, what will happen? It will break into smaller bundis. So that's where you can treat this as an analogy. Similarly, here what happens is these vortices interact and say disturb themselves. It will break into smaller and smaller blobs, such that the breakage of big vortices into smaller vortices happens rapidly, and this disturbances die down eventually. That's where these grids are useful in breaking down the vortices or eddies into smaller one, and it will try to dissipate. That is, it will try to completely eliminate it from the flow field. That's where grids are useful. So to simply say, grids can remove large scale fluctuations or large eddies and break down into smaller ones, and then finally eliminate it. So in simpler aspects, what I can tell from the honeycomb part and grid part is, honeycomb is essentially to remove the swill flow, and grid is essentially to remove the turbulent flow. So one way we can remove the eddy part. So there is one more part which we need to discuss. That's where I have this contraction section. So this contraction section, you might find the area is reducing in this section. So you have typically a higher intake. At the end, you might have a smaller outlet. So the area reduction is helpful in doing our core business. This is reduction of turbulence. So you have to know what is turbulence, because I didn't introduce turbulence in the earlier place. So I will tell some aspects of turbulent flow. If you consider a laminar flow, which might be moving as laminates, this is layer by layer. And if you consider a turbulent flow, which might be randomly fluctuating, so it can form three-dimensional vortices or eddies, like rotating blobs of fluid, rotating pipes of fluid, rotating filaments of fluid, randomly fluctuating fluid. So it has multiple characteristics and completely a three-dimensional flow. So we want to reduce this fluctuating characteristics. That's where we are using contraction section. So typically on the left side, what I have shown is a typical fluid blob. Why I have shown it like arrows is, the fluid blob might be moving like vibrating in this way. This is fluctuating in this way, horizontally or vertically. So the fluctuations can happen in three dimensions. So I have shown only a two-dimensional aspect here. So you can extend it to three-dimension aspect across this screen. So the first part is, you have a fluid blob. Don't think about the scaling aspects here. Just for representative purpose only, I have made this particular schematic. So this fluid blob, it might be fluctuating from one point, holding that as a point, moving from left side to right side. In this direction, the flow is moving, and this might be doing this fluctuation on vertical axis and also in horizontal axis, maybe in also the z axis, which is perpendicular to the screen. If this fluctuating fluid blob or fluid element is moved through this contraction section, you might find multiple fluid blobs here and there, and these blobs will find lesser space. For example, you have a passage which is 2 meter wide, and you are typically hopping to the left side, hopping to the right side for 1.5 meter width, like how kids play, and then you keep moving forward. And the passage is typically 2 meters, so 1.5 meter is sufficient for you to hop to left and hop to right, and then to move forward. It is comfortable for you. Now what I do is typically reduce the passage, that is the width, from 2 meters to 1.5, then 1, and then to 0.75, exactly to a place where only a person can move. Then your hopping stops at the end. So when your passage gets reduced, you don't have a space to hop to the left or right. That's where your disturbances are brought down. That's where if you move from left to right, the area reduction is seen here. This is not allowing the fluid blob to, say, fluctuate in multiple directions, and that's where the fluctuations come down. So once the fluctuations come down, you have least fluctuating output fluid flow. So that's where typically we can treat it as fluid flow is less and less turbulent. So the other aspect of turbulent flow is, like, if you have least turbulence in the flow and if you leave it to move further, the flow will eventually become laminar flow, which means the turbulent flow has lost its energy and it has become a laminar flow. So why I am saying like this is, you can correlate this with your Reynolds number. Reynolds number typically has a formula, velocity scale, length scale by kinematic viscosity. So keeping this length scale and the viscosity constant, you can play with velocity, or you can keep the velocity and fluid parameter constant, and you can play with your length scale. The length scale is typically the size of the eddies, or we can consider a characteristic length. Here it might be, this might be the characteristic length, the output, and you might find this diameter of the fluid blob or the eddy. You can consider that as a length scale for that particular blob, which is a local length scale. And now if you see this, when you have a higher energy, which means the fluid can move faster, the velocity might be higher. In terms of kinetic energy, half rho u square, you can see that how much the energy the fluid possesses. So when this energies are coming down, your fluctuation also will come down, finally dissipate into heat. So that's where this contraction section essentially cuts down the turbulence, and then it gives the least turbulent flow as an output. So this is a typical example I have given here. But a typical wind tunnel, if you see, that contraction section will be of polynomial profile. So you might have seen the shape in the previous slide where I introduced a typical subsonic tunnel. So that particular contracting shape, why people are using is, like, if you axially, this is if you see this particular say particular plane of this contraction section is applying stress on this particular fluid blob in this direction, that is from top to the center, and also this wall is applying shear from this wall to this center. So as you move from this part to this part, you are stressing the fluid element. So if you are stressing the fluid element, the fluctuating component also will come down. So if you are stressing it in a linear way, the reduction of turbulence will be something. If you stress it exponentially, the uh, the behavior of turbulence or the decay of turbulence will happen faster. So that's where you find typically people using that kind of exponential profile, or this polynomial profiles. So coming to typical examples, I told you about tabletop wind tunnel, which we fabricated in our laboratory. Thanks to Bunni, Rakshantha and Sanjana, these three people did this job when they were doing their bachelor degree. and this was applicable for a particular aspect of combustion phenomenon. So I will go into the basic schematic. So why we wanted to go for a tabletop tunnel is typically we had a lesser space in a particular room allotted for us. That was a visualization lab. It was typically like a 10 cross 10 foot room, and we had a smoke tunnel there, and there was another particular experimental setup. So we had a leased space where 2 meter cross 1 meter table was allotted for us. So within the table, we had to create a wind tunnel where we have to study some particular combustion aspect or flow over a particular material which is burning. So we had to generate a flow. That's where our basic requirements are. We had to have a typical test section which should be allowing us to see through, wherein we have to do visualization, and the flow should be somewhat conditioned. And so we require a flow conditioning unit, and then we have to have a source of flow. That's where we had placed this axial fan. So typical schematic, a hand sketch initially we started with, and then we had a fan, and then we have this contraction section to reduce this turbulence, and then we have this honeycomb structure to reduce the swell flow, and then we have a test section here to keep the model which is burning, and we can visualize using this glass section placed here, and typically there is an outlet, and then after this we have a diffuser. I didn't tell you about the diffuser. Diffuser is just to allow this flow out of the tunnel towards the ambience such that the pressure is matched. Then moving further, I will show how this schematic was realized as a real wind tunnel. So first we decided what kind of fan we have to use and what will be the typical flow rate, and if we know the area of the test section, from the flow rate we can easily calculate what will be the velocities. So we worked slowly on that, and then decided what kind of components to be used for the fabrication purpose. So since it was a smaller tunnel, which is a tabletop device, so we decided to go ahead with say materials which we can purchase from a typical hardware shop. So that's where I go to the next slide. You can see on the left side, this is a typical fan which we used. You might have seen this fan in places like restrooms where people use it for exhaust purposes. So this gives a decent flow which can create suction also, which can be used for blowing air into ducts. So that is the typical part we purchased from a hardware shop. Then the next part is you are seeing this particular mid picture. This is the duct within which honeycomb structure is placed. This honeycomb structure we made it by ourselves, wherein we used straws made of paper, and we stacked it completely, and then pasted with quick fixed glue such that it will be held in that particular position. We didn't use plastic straws since it was banned. So the available paper straws were used for this. Also, if you want more stable and if you want for longer duration, I think when you are designing, you can go for metallic tubes of a particular aspect ratio, and you can use it as a honeycomb structure. And the third picture on the right, which you are seeing here, is the typical mesh, this mosquito mesh, which is available again from hardware shop, and it has like a wire of 1 mm thickness, that is 1 mm diameter, and it is separated by
1.5 mm such that it will allow possibly flow through this, and this was kept after this particular honeycomb to filter out the turbulence. And then after this honeycomb, once the flow is conditioned, we have the test section which is shown on the left bottom picture. This is completely made up of a wooden frame, that is a plywood, and we had glass on 3 sides. This is on that rear side. On the frontal side also glass with the opening facility, and also on the top side with the glass to allow some light to pass in to the domain and to show what is happening inside that particular test section. And finally, since our application was to study about the combustible material, we created a structure which is shown on the right bottom side. This is a typical wooden stand wherein some treatment was done, and then a metallic cup was placed inside that wood, here exactly on the bottom of this place, and then an incense material, typically a doop stick, which is a form of a solid which is available from any basic shop. This typical incense material was kept inside that particular wooden stand, and then it is ignited from the top, and then it is placed inside this test section for experimentation purposes. So this is about the parts of the wind tunnel and how we are going to see the fabrication is. The result is here. It was completely done with plywood, like first designing the parts individually and then cutting it and then fixing it with screws. You might find all screws for fixing the wooden planks, and then finally this fan was placed on the right extreme side, typically of this side, and you might find a typical regulator which is the potentiometer to control the speed of the fan to have a controlled flow. And exactly inside this place the honeycombs are seen, and you might find a grid here, and this is a typical window for say allowing people to open the test section to keep the material inside to handle it, and this is the tube which is the extension which is to be connected to the outlet or the diffuser. And this outcome was presented in a conference, and it is about to be published soon. So, with this type of wind tunnel, which is a tabletop one can do some basic studies. So, our application was about to study combustion. So, we had a typical simple wind tunnel. We didn't go for complex profiles, which was fabricated within a week. So, I will show some of the outcomes from this. So what we did is, before that I have to tell what exactly we did is, we took the incense material, we ignited it, we kept it on the bottom base plate and kept it inside this test section, and from the top side we shined the laser, and then we viewed from this particular window, took videos using a high-speed camera, and then post-processed the image to get the results. So moving ahead, I am showing the results. So this is a particular sample result which we got by burning a hexagonal incense material. The flow is from right to left. You can easily see that there is a wake region formed behind this burning material, and the time instances are shown from left to right. The initial stage of burning is happening here. So the flow is allowing say allowed from say right to left, such that the flow comes here and then it moves over this body, and then has a recirculation zone on the rear side, and then it leaves that particular body. So this is how the flow is happening. So typically on the front leading edge side you might find a stagnation happening, which means the incoming flow will have more and more oxygen, such that it can enhance the burning rate. That's where this particular point, if you track it for all these things, you might find the highest burning has happened on that particular stagnation point, and the least burning has happened on the rearward side or the aft side. So, effect of flow on combustion was studied, and you might see pictures in green color. This is typically because of the laser which we used, like 532 nanometer laser with a particular glass rod. That creates a sheet, and then we had a camera which was a microscope camera which can zoom into the particular level wherein we can see the exact vortices or the shape of the say flameless reacting material or reacting medium which is moving through the material. That's where these visualizations were done. I think this results also was presented in a conference, and it's to be published soon. Moving ahead, we have another example. It's atmospheric boundary layer tunnel. Thanks to Murukesh, Akhil and Saneesh, these three people came up with a huge wind tunnel, and this is stationed in our hangar, and it was about a cost of 6.5 lakh rupee. And Murukesh is here online, joined with us to help you with queries which we have about this tunnel. Let me go ahead and show you how these people did and what is the physics behind it. So the basic requirement for this particular atmospheric boundary layer tunnel is about atmospheric boundary layer. First we should know what is atmospheric boundary layer. Typical wind tunnels will have uniform profile, which means the velocity is uniform, and if you see this particular profile, the velocity is increasing with respect to height. So the bottom layer is the ground above which you find all buildings, trees, and then terrain, especially you are seeing the terrain, and when you have flow over this terrain, this bottom disturbances might create a highly turbulent flow. This is what is mentioned here, and then as you move up in atmosphere, this turbulence goes down and you might find like a laminar flow. So to create this kind of profile inside a wind tunnel, it is a little difficult because it needs the length to develop a boundary layer into completely turbulent zone. So typically if you see a subsonic wind tunnel, it will be of a length, and if you want to develop a atmospheric boundary layer tunnel, it will be lengthier than what you are typically seeing in your laboratories. So that's where taking this into account, we started designing this particular tunnel, basically calculating the flow requirements, what is the test section size, and then we move ahead with the structural part. So this was the initial design which Murukesh and their team did, and you might be seeing a CATIA design here. The green color part is the intake and the flow conditioning part, green, and this is the first section, and then you have this particular section wherein this development of boundary layer happens, and this is the test section part, and again you have a constant area duct and you have a diverging duct connected to a housing where a motor is placed with a fan. So this view might be appealing to people who are seeing this slide, and you can see how the design of the tunnel was done. And with this tunnel in mind, we went ahead with the initial fabrication process. So like first we have to decide how the structure is to be made. That's where we came up with the idea of using aluminum structures. That's where commercially available this frame structure was made by purchasing profile channels, which is shown on the left extreme side. These are aluminum profile channels which are available in market. Directly you can purchase this, and it can be connected using these brackets, using this joint clips which can be threaded, and you are typically seeing this frame made by our group. And first after finishing this frame, people started working on the outer structures, that is the walls of the wind tunnel, and then move ahead in other aspects. Like this slide will explain you what are the phases which our group had gone through. Like after creating the structure, we had say a bunch of planks, that is plywoods, which was strengthened, placed between this profile channels, because the profile channels has groove to accommodate this wooden planks, such that the complete outer structure was made. And once the outer structure was made, the honeycomb structure was also made, and this is shown in the other slide. I will explain about that. And once the complete structure was done, then carpeting was done inside the particular tunnel to produce the rough surfaces, and this will enhance the production of the turbulent boundary layer on that particular carpet surface. So then this wind tunnel test section was fixed with the glass. A complete single piece of glass was held between this particular aluminum frame, and it was on the three sides such that it can allow visualizations to happen. Also you might see that there is a person who is moving from the bottom side, because there is a opening where a person can go inside from the bottom, inside the test section, to place the model or fix the model, turn it. So whatever manipulations you want, you can go inside and you can do it. That's how the wind tunnel was designed. It was like 1 meter cross 1 meter test section, and so you can house typical models of size more than 30 centimeter. So after building the structure, we moved ahead to build honeycombs. For building honeycombs, either we have to go for metallic structures or commercially available products. That's where we decided to go with plastic PVC pipes, so which is easily available from plumbing or hardware shops. So we took pipes which is used for electrical wiring thing in buildings. So this pipe was cut at a particular aspect ratio and stacked it, and then strengthened and stuck together with say quick fix glues, and then we had a typical mesh structures which is shown on the next slide, that is this present slide. On the left picture you might see a typical mesh structure. Again, it is a mosquito type mesh, and it was a metallic mesh. It was fixed to a frame of 1 meter cross 1 meter, slightly less than that, because it has to fix inside the wind tunnel. This is to reduce turbulence. And on the right side you might see a finished test section. In front of that you might see also a fan, and this is a typical model which was kept inside the wind tunnel to test about its aerodynamic properties. So the flow of the wind tunnel, that is the flow source of the wind tunnel, is made available using axial fan, which was purchased from Nadi fans, and you might find these kinds of fans which are typically available in industries. There are two choices which we had for this source of flow, like having multiple smaller fans and then stacking it up in the end side of the wind tunnel like a grid or mesh, and then controlling all the fans, which is a difficult task. So we have to come up with a control unit. On the right side you are seeing flow conditioning unit, a typical controller, which is like a frequency control device. So you can control the RPM of this fan such that you can have different velocities. So this is a typical source which we have used, and this is the completed atmospheric boundary layer tunnel, and we had tested a few models. I am not showing results here due to the shortage of time. So this tunnel is presently useful for people to study about flow over different objects like buildings, wind tunnels, terrains, and then typical streety structures with vehicles on roads or something like that. So with this, I thank you all for patiently listening to me for an hour, and I hope I have given a brief introduction to what is a wind tunnel, what are the parts of a wind tunnel, and what is the physics behind each and every part. And then I gave a couple of examples how we build a tabletop wind tunnel and a atmospheric boundary layer tunnel. I have not shown calculations here, but you can ask us, we can be able to share it with you, or you can refer to our papers which will be published soon, so that will bear the calculations or the formulas, and I will be happy to answer questions from your side. The session is open for discussion now. Thank you for patiently listening once again.